Imagine you're a pilot on a routine flight. Suddenly, your navigation screen glitches, and it shows your plane is thousands of miles off course, hovering over an ocean when you should be landing. Sounds like a sci-fi movie, right? But it's not. It's a real and growing threat called GPS spoofing, where the signals we all rely on are hijacked and replaced with fakes. Our entire modern world, from shipping and aviation to financial markets and your Uber driver, is balanced on a fragile system of signals beamed from about 12,500 miles up in space. And that system is terrifyingly easy to break. But what if we didn't need satellites at all? What if you could know your exact location, anywhere on Earth, using just the fundamental laws of the universe? Scientists are now harnessing the weird and wonderful rules of quantum physics to build a device that could make GPS obsolete. This isn't just a simple upgrade. This is a total reset, a new way of seeing the world that is un-jammable, un-spoofable, and unbelievably precise. This is the story of the quantum leap that will end GPS as we know it. The Achilles heel of the modern world. To really get why we need to replace GPS, you first have to appreciate just how much we lean on it, and how vulnerable it's made us. The Global Positioning System is, without a doubt, an incredible piece of technology. A constellation of satellites, each with a hyper-accurate atomic clock, zips around the Earth, constantly broadcasting a time signal. Your phone, your car, or a plane's navigation system listens for these signals from several satellites at once. By calculating the tiny differences in when those signals arrive, it can pinpoint its position on the planet. It's brilliant. And it works, until it doesn't. The problem is, by the time those signals travel over 12,500 miles to Earth, they're incredibly faint, weaker than the universe's background radiation. This makes them shockingly easy to disrupt. A cheap, low-power jammer can create a bubble of no GPS, dozens of miles wide, knocking out everything from commercial drones to emergency services. Even scarier is spoofing. This is where someone doesn't just block the signal, but broadcasts a fake, more powerful one. All of a sudden, a cargo ship thinks it's miles off course and corrects its path, steering it right into danger. An airliner's autopilot could be tricked into thinking it's on the right glide path when it's actually flying toward a mountain. And this isn't just a theory. Military conflicts have seen widespread GPS jamming and spoofing, and the tech to do it is getting cheaper and easier to find every day. And this doesn't even cover the system's natural blind spots. GPS signals can't get through rock, dense buildings, or water. That's why you lose your signal in a tunnel and why navigating the urban canyons of a city can be a nightmare. For a submarine, it's a massive, constant headache. To get a GPS fix, it has to get close to the surface, making it vulnerable to detection. Even a giant solar flare could, in a worst-case scenario, knock out the entire satellite network, plunging our world into logistical chaos. Our dependence on this single, fragile system is a huge vulnerability. The world needs a backup. It needs something better. The solution forged in the quantum realm. So, what if the fix wasn't a better satellite or a stronger signal? What if we could get rid of the signal entirely? What if a device could know where it is and where it's going just by looking inward? This is the promise of quantum navigation. It's a technology that doesn't listen for any external signal. No satellites, no radio towers, nothing. Instead, it measures its own motion, its acceleration, its rotation, every change in direction, using the bizarre and almost magical properties of atoms at the quantum level. Picture a black box inside an airplane. That box knows its exact starting position. From that moment on, it feels every tiny movement the plane makes. It feels the push of acceleration on takeoff, the gentle bank of a turn, the subtle shifts from turbulence. By constantly adding up all these movements, it can calculate its new position with unbelievable accuracy, without ever once asking a satellite, "Are we there yet?" This basic idea is called inertial navigation, and it's been used for decades in submarines and missiles. But traditional systems have a big problem: drift. Tiny, microscopic errors in their mechanical gyroscopes and accelerometers build up over time. After a few hours or days, the calculated position can be miles off from reality. This is the problem quantum navigation solves. By swapping out mechanical parts for the fundamental properties of atoms, it promises a level of precision that's hard to wrap your head around. It's so accurate that it basically creates a perfect, internal map of its own journey through space. So, how on earth does it work? To understand that, we need to shrink down to a world that's unimaginably small and unbelievably cold. How to build a quantum compass, the heart of a quantum navigation system, is straight out of science fiction. To make one, you first have to create one of the strangest and coldest states of matter in the universe, a Bose-Einstein condensate, or BEC. Here's the idea. Inside a small, vacuum-sealed chamber, scientists trap a cloud of a few million atoms, usually something like rubidium. Then, using a bunch of lasers, they start to cool these atoms down. And when I say cool, I mean cold. Colder than deep space. We're talking temperatures just a fraction of a degree above absolute zero, the point where all atomic motion is supposed to stop. At this insane temperature, something amazing happens. The atoms quit acting like tiny individual particles and start acting as one. Their quantum waves, which are normally microscopic, overlap and merge until the whole cloud behaves like a single, massive quantum object. They become a Bose-Einstein condensate. The best analogy is a light bulb versus a laser. A light bulb spits out photons of light randomly, in all directions. It's chaotic. A laser is coherent. All the photons march in perfect lockstep. A BEC is like a laser, but for atoms. And this coherence is what makes it the perfect tool for measurement. Now, with this ultra-cold cloud, the real magic starts. This part is called atom interferometry. It works a bit like noise-cancelling headphones, but for motion. Using a precise laser pulse, scientists split the wave-like state of each atom in two. Thanks to the bizarre rules of quantum superposition, each atom is now traveling along two different paths at the same time. It's a mind-bending concept, but it's a proven reality. A second laser pulse guides these two paths back toward each other, and a third pulse recombines them. Here's the crucial part. If the device is perfectly still, the two atomic waves recombine perfectly. But if the device has moved, if it has accelerated or rotated even a tiny bit, the two paths will be slightly different. When they recombine, this difference creates a measurable interference pattern. By reading this pattern, the system can calculate its own movement with staggering precision. It is literally using individual atoms as the world's most perfect rulers. A new era of precision, so just how precise are we talking? The potential here is staggering. Lab research suggests quantum accelerometers could one day be thousands of times more sensitive than the best systems we have now. The goal is to build a quantum navigation system that could, in theory, operate for weeks on end and have its calculated position drift by less than a meter. Imagine a submarine, deep in the ocean, knowing its exact position to within the length of a dinner table after a month underwater, all without a single signal from the outside world. This is exactly why defense agencies are racing to develop this technology. The UK's Ministry of Defence has funded the development of what they call the world's first quantum compass, a self-contained unit that doesn't rely on GPS. The US is also heavily investing in these systems as the ultimate solution to jamming and spoofing. The key is that the system is entirely self-contained. There's no signal to jam or spoof. Its navigation is based on the unchangeable laws of physics. It is fundamentally tamper-proof. And this technology is quickly moving out of the lab. In a major milestone, a team involving the company Inflection and Bay Systems successfully created and maintained a fragile Bose-Einstein condensate aboard a flying aircraft, proving the core component can survive the rigors of travel. Other researchers have tested early versions of a quantum compass on a shaky commuter train in London, showing it could provide accurate positioning when GPS failed in tunnels. This isn't a distant dream, it's a functioning technology being tested and proven right now. We're at a fascinating turning point, moving from a system of external signals to one of internal truth. It's a huge leap, and it makes you wonder what other technologies we take for granted could be completely upended by quantum physics. Let me know in the comments what you think the next big quantum revolution will be. It's always great to read your ideas. The bumpy road to a GPS-free world. Okay, let's pump the brakes for a second. While quantum navigation is the future, you won't be finding a quantum compass in your smartphone next year. There are still some pretty big hurdles to clear. The biggest challenges are size, complexity, and cost. The gear needed to create a Bose-Einstein condensate, the vacuum chambers, laser arrays, and magnetic traps, is currently bulky, power-hungry, and incredibly expensive. We're talking lab-sized equipment, not something you can slip into your pocket. While great minds are working on shrinking these components down, we're still a long way from mass production. Then there's the environment. A quantum sensor is, by its nature, one of the most sensitive instruments ever made. That makes it really vulnerable to vibrations and temperature changes. As the team who tested their quantum system on the London train noted, trains are shaky, and quantum sensors are delicate. Their clever solution was a hybrid stack that used rugged, traditional sensors to handle the big vibrations, letting the quantum sensor do its delicate work in a protected bubble. This points to the fact that the first real-world users will likely be hybrids, mixing the best of old and new tech. So while the promise is immense, the road to a fully quantum-powered world is an engineering marathon, not a sprint. The first users will undoubtedly be high-stakes players, the military, aerospace, and deep-sea exploration, where the massive cost is justified by the need for un-jammable navigation. The new navigational ecosystem. So, is GPS truly dead? The answer is a bit more complicated. It's not that GPS will just disappear. Instead, we're heading into an era of navigational diversity. The weaknesses of GPS have become so obvious that a whole ecosystem of backups is rising up to make our global system more resilient. One of the most promising ideas is the rise of LEO satellite constellations. LEO stands for Low Earth Orbit. Companies are launching thousands of small satellites that orbit much closer to Earth than GPS satellites, hundreds of miles up instead of over 12,500. This proximity means their signals can arrive at Earth up to 1,000 times stronger than GPS signals, making them harder to jam and better at penetrating buildings. Then there's a ground-based backup called Aileron. Instead of space, Aileron uses a network of powerful, land-based radio towers. The signal is a staggering 3 to 5 million times stronger than GPS, making it almost impossible to jam on a wide scale. Even regional systems play a part, but they also offer a cautionary tale. India developed its own system, NAVIC, to provide navigation over the Indian subcontinent. However, in March of 2026, reports confirmed that the atomic clock on a key satellite failed, leaving the system operating below the minimum number of satellites needed for accurate positioning. It's a powerful reminder that any system relying on a few expensive assets in space is inherently fragile. The future of navigation isn't one technology replacing another. It's a future of layers. A future where your device might seamlessly switch between GPS, LEO satellites, and Aileron, while for the most critical jobs, an internal quantum compass provides the ultimate, unshakable ground truth. We are standing on the edge of a navigation revolution. For half a century, we've looked to the stars to find our place, relying on a delicate web of signals from space. That era of total dependence is ending. The clear and present dangers of jamming, spoofing, and system failure have forced our hand. In the short term, that means a smarter, tougher network of satellites and ground-based backups. But the long-term future, the true quantum leap, belongs to a technology that needs no external signals at all. A technology that finds its position from within, using the fundamental dance of atoms cooled to the very edge of existence. Quantum navigation represents the ultimate freedom in navigation. It's a system that's un-jammable, perfectly precise, and works anywhere, from the deepest ocean to the far side of the moon. The journey to shrink this incredible power and put it in all of our hands will be long. But the race is on, and the breakthroughs are happening faster than anyone predicted. The little blue dot on our screens isn't going away just yet, but its days as our only guide are numbered. The next map is being drawn not in space, but inside the atom itself. The implications of this are massive, from truly autonomous vehicles to exploring deep inside the Earth. So I have to ask, what do you think about this quantum leap? What's the most exciting, or maybe the most concerning, application you can imagine? Let me know your thoughts in the comments below. And if you want to stay ahead of the curve on the technologies shaping our future, make sure to subscribe and hit that bell. Thanks for watching.